public outreach. And if you walked in today, you came in and hopefully you got one of these, the lithograph that we have for you tonight. This one is of the Veil Nebula, which is a piece of a supernova remnant. It's actually a very small piece. I believe this is in the area called the broom handle, of the handle of the witch's broom in the Veil supernova remnant. On the front, you see the Hubble picture, and on the back, there's a context picture to show you what a small piece of the supernova remnant that it is. And this, of course, relates to tonight's speaker's topic, the death and afterlives of massive stars. Our speaker, Dan Milisavljevic, close enough? Yeah, okay. From Purdue University. Upcoming, as you know, this one was delayed several weeks because we had such a special speaker for the conference that's here today. So the next one will only be 2 weeks away. May 7th, Jolene Karlberg, The Fiery Fate of Exoplanets. And then we go back to our normal once-a-month schedule. In June, Chris Britt, also of the Office of Public Outreach, a colleague of mine, can pulsar recycling produce a gamma ray excess? You do recycle your pulsars, don't you? Okay. Well, actually, the universe might be recycling its pulsars, okay? And you can see what that does. And then in July, on July 2nd, Joe DePasquale, our new, relatively new astronomical image processor, will talk on the art and science of astronomical image processing, okay? If you want to find out the schedule, you go to your favorite web browser, your favorite search engine, and type in Space Telescope Public Lectures, and you should find this web page. We have a Go link, hubblesite.org Go Talks, where you can see on the right side, we have the list of the upcoming. On the left side, we have the links to the live, both on our webcasting and on YouTube, as well as our archive on YouTube and on the STSCI webcasts. Finally, you can, of course, subscribe or unsubscribe to our email list, which sends out about 2 or 3 emails a month telling you just what's up and coming. The email announcements, you can sign up at the website. There are, however, some people who don't like to do that. You can just write down your email address and give it to me, and I'll make sure you get on there. If you have questions, the email address is publiclecture@stsci.edu. Our social media for the Hubble Space Telescope, the upcoming James Webb Space Telescope, and for the Space Telescope Science Institute are here on Facebook, Twitter, YouTube, and Instagram. If you want to hear more of my spew, you can see what I do on Facebook and Twitter, although I only do that occasionally, not all the time. All right. The observatory will not be open tonight. He saw the clouds moving in and he said, sorry, we're just not going to have a clear night view. But as always, if you go to md.spacegrant.org, you can find this page for the Maryland Space Grant Observatory. On Friday nights, they do observing. If you check there at Friday night at 6 or 7 p.m., they will have posted whether or not they're going to be open on Friday night to do observing, and you can come down and do that, okay? All right. And now the news from the universe for April 2019. Our first story tonight, Hubble's 29th anniversary. Today is April 23rd, and 29 years ago today, tomorrow is when Hubble launched, April 24th, 1990. And of course, every year we have to come up with a interesting press release for you. And, sometimes it gets harder and harder to top ourselves, okay? So we went in an interesting direction this year, okay? We wanted to remind you something very important about Hubble observations. Now, who here has heard of the Crab Nebula? When you think of the Crab Nebula, you think of this. And this is a supernova explosion that our speaker tonight might mention in his talk. But this is what everyone thinks of the Crab Nebula. But there is also another Crab Nebula. Okay? This is a supernova explosion, a star that exploded, blew its guts out into space. There is something called the Southern Crab Nebula. And this is an image from Hubble from 1999 in a nitrogen filter. Okay, this is not a supernova explosion. This one, and by the way, whenever we say, oh, it's the Crab Nebula, it's supposed to look like a crab, just squint your eyes a little bit, okay? Then you might be able to see it. Honestly, this one looks a little bit more like a tick, okay, than a crab to me. But, shh, don't tell the guys who discovered it, who knew, or at least who named it, okay? So this was back in 1999, and it was done with Wide Field Planetary Camera 2. Can we take the lights down a bit? There's a lot of scattered light on the screen. There you go. So now you can see in the center, you can see this cutoff of the edges. That's characteristic of the WIFPIC 2 footprint, okay? So we were going to come back and do this again, and I'm going to reorient it for a little bit there. Okay, and then we went and redid this. We also did the nitrogen filter, okay, but this time we did it with Wide Field Camera 3. So this is the nitrogen filter that we did. We also did several other filters. We only had one filter on this in 1999. We did the oxygen filter, okay, and we did the hydrogen alpha filter, and then we did the sulfur filter. So we have 4 very specific observations that are these very tiny filter band passes, all right, that only pick out the emission from specific elements, okay? And together, this was our release that we came out with last week. All right, this side go ooh, this side go ah. Thank you very much. All right, if we're going to do this, we got to do this. All right, so this is the Southern Crab Nebula in 4 specific filters. And you can see how, like at the end of the crab's legs, how it gets green, okay? Well, that indicates that there's only specific emission in there versus the other colors. You can see how colorful it is, but those colors really mean something to astronomers, all right? Now, this is what we call a protoplanetary nebula. Okay, you may have heard of planetary nebula. It's an end stage of a star where it blows off, and a nice wind blows off its outer layers into interstellar space. Well, what we believe is going on here is that there is a evolved star, well, actually a stellar remnant, a white dwarf, and then a dying star, a red giant, and they're in orbit around each other in a binary system. And this red giant is giving off some gas. It hasn't quite gotten to the planetary nebula stage. That's why it's protoplanetary nebula. And some of the material has formed a disk around them, stopping the flow in this direction, but letting the flow go in perpendicular to the disk. So that the flow that you see is coming out in 2 bubbles, one here and one here, that sort of resembles an hourglass, where it's pinched at the center and bulbs going above and below. And so this is a protoplanetary nebula. It probably will become a full-blown planetary nebula a few million years from now, okay? All right, now, what we really wanted to do was remind you of what we did to see all these different features of it. So one of actually, I think the more important, besides the image, is this diagram that takes the Southern Crab Nebula, breaks it up into those 4 filters, and then relates those 4 filters to a spectrum, okay? So this spectrum was taken of the inner region here, and it shows the full emission across the various wavelengths of visible light. To remind you that, Hubble gets a lot of its science done by imaging, but it gets just as much science done using spectra. This spectrum that we're showing here, I know it's not the pretty pictures that you're used to with Hubble, but 50% of Hubble's science is done by examining these spectra and looking for the temperature and the composition and the motion of these individual elements of gas to really get the details of what's going on. So it's a combination of both the imaging and the spectra that produces the Hubble science that has advanced astronomy so much. Now, this is a visualization done by our department, just to sort of get that point across. Here you can see that spectra taken of that central region, pulled out into the full spectrum. And then we take the individual images and correlate them. And that is just one example of how both imaging and spectra work together to get us the science that we do with Hubble. Our second story tonight, you might have guessed, I'm sure you've all seen this before, but hopefully I'll tell you a few things that you didn't hear, at least from the mainstream media. The black hole in Messier 87. Now, first of all, what is Messier 87? It is a giant elliptical galaxy at the center of the Virgo cluster. It is I think it may be the largest galaxy in Virgo. It's one of the largest galaxies in Virgo, okay? It's a giant elliptical, all right? And this is the Sloan Digital Sky Survey. And down at its core, it has a supermassive black hole. And you can sort of see it in the center of this image, but if we take the Hubble image, and then we zoom in on that Hubble image, you start to see this jet coming out of the center. Let me zoom in one more time. All right, now you can definitely see it. Okay, so there is a bright spot in the center, which is where the supermassive black hole is. And the material around the supermassive black hole is spewing out some material at such speeds that that material is extending across 5,000 light years of space. Okay? Yeah, so we're seeing this jet here. And it's actually kind of cool. If you look at this in infrared, I have a friend who works at Spitzer, and he said, yeah, but in infrared, we can see the jet on the other side. Do you see the jet? In the Hubble image, you can't see the jet on the other side. But the infrared image, it does glow in the infrared, and you can actually see it. It was really kind of cool. We were comparing images. But you see that bright spot way down in there is the supermassive black hole. How far down in there? I wanted to know. So I put together this series of images. All right, so I had to go from Hubble to the radio. This is from the Very Large Array, radio at 2 centimeter, and we zoom into that. And then we had to go to another radio image from the VLA at 7 millimeter. And then we had to start using arrays of telescopes, very long baseline interferometry. This was 18 centimeter observations here, right? And then we had to go in even further using another very long baseline array, but this was back at the 2 centimeter thing. And then we had to go using more very long baseline array at 43 gigahertz. And then at the 43 gigahertz, we're going to zoom in on this yet one more time. And finally, we're down to just the emission from the material around the black hole. And see that tiny little black spot there? Zoom in, and this is the image of the black hole at the core of Messier 87. Now, it's not actually the black hole, okay? Because face it, black holes are black. No light can escape them. They cannot emit any light by definition, okay? So this is not an image of the black hole. It's an image of the stuff around the black hole, okay? So this is, the event horizon is in here. The size of this dark region here is about 1.5 to 2 times the event horizon of the black hole. And the event horizon is the actual edge. And when around that black hole, okay, come on guys, let's turn off the phones here. Around that black hole, so space is warped so much that light actually starts circling around the black hole. There's a photon sphere and such. And light gets warped around it and stretched around it and pressed around it. And we can predict what it would look like. And actually, we predicted it would look pretty much like this, okay? Now, how many people saw the movie Interstellar, right? And there was a somewhat scientific visualization of a black hole in Interstellar. And it looked a lot better than this, but then again, it was CG. This is real, okay? This is real. And if you take that Interstellar one and you fuzz it out into the resolution so that you can't see it, it actually looks a lot like this, okay? All right, so this is what was basically what was predicted. General relativity has been really, really good at predicting what we were going to see. You saw how many times I had to zoom in order to show you this. This resolution is 2,500 times greater resolution than the Hubble Space Telescope. Yeah. How did they achieve that? They used 8 radio telescopes across our entire planet, one down at the South Pole, others spread out around the world, to basically synthesize a telescope as large as our entire planet. Okay? Now, it doesn't have the collecting area of our entire planet, but it can achieve the resolution of a telescope as large as our entire planet. So this is basically about as good as we can do, okay? And this black hole is 55 million light years away. And you know what? Its size is about the size of our solar system. That's the size of Neptune's orbit compared to the black hole. And the event horizon of the black hole. And so being able to resolve this black hole is analogous to being able to see a quarter on the surface of the moon. This is one incredible achievement here. Yeah. Now, there's only one problem with this, all right? Is we've already created a telescope as large as our planet. It's kind of hard to create one larger unless you start sending telescopes out into space for interferometry. And, well, that's not going to be solved anytime soon. The second problem is that if you've seen one black hole, you've sort of seen them all right? They're going to get better at this. But the photon sphere and all this photon wrapping around it isn't going to change that much. What's going to make the next observations interesting is, one, they're going to look at the black hole at the center of our galaxy. That'll be kind of cool. It may look very similar to this, but at least, it'll be our black hole, not one from some other galaxy. So we'll have a sense of priority. And two, they want to be able to watch these over time and see the undulations in the photons that are happening. They want to see the changes in the emission from around the black hole. And that will start to tell us more. So just like we started to have a new field of astronomy with gravitational wave astronomy a few years ago, this is the beginning of using interferometry to actually see and study black holes up close and personal. All right. So just to remind you, here is that zoom in, but with a little bit of piano music. So really, I just put this together afterwards to try and understand it for myself, and I knew I'd want to show it to you guys here. And then I just threw it up on YouTube, thinking that, all right, well, maybe other people would like it. It's our second most popular video of the last 9 months. So obviously, we provided a little bit of context that was necessary for tonight. All right.
I saw that on YouTube last week.
You did? Yeah. Great. So thank you for watching. And now let's go to our featured speaker tonight. Dan Milisavljevic is from Purdue University. And I did not get a chance to get his resume before him. So I will let's introduce him to you and let him tell you all about himself. Ladies and gentlemen, Dan.
Well, Frank, thanks very much for the introduction. You are a difficult act to follow. You have lots of energy. I hope I can match it in some scale. Now let me just get set up here. Make sure that we're live. Oh, and that didn't work. Don't look at my password. Okay, there we go. All right, it truly is a pleasure to be here at the headquarters of some of the most important scientific instruments ever designed by humankind. Like a kid, I've always admired the Hubble Space Telescope, and so to be here today talking about my use of the Hubble Space Telescope and other space observatories is truly a pleasure. As was mentioned, we're having a scientific meeting right now where a lot of experts are getting together to talk about some of the phenomena that I'm going to be reviewing in this talk, and I've tried my best to incorporate their science, although there is a lot. Yes, I'm Dan Milisavljevic, currently at Purdue University at the Department of Physics and Astronomy, and I'll be talking today about the deaths and afterlives of massive stars. The workshop we're doing over the last couple days is the deaths and afterlives of stars. So just to narrow down the focus a little bit, because there are a lot of stars, I'll just be talking about massive stars. And this picture is chosen in particular. You're going to see it a lot. The name is the supernova remnant, Cassiopeia A. It'll be the poster child for a lot of what is to follow. I'm here alone up front here, and yet I am backed by a whole legion of supernova superheroes that help me on a daily basis. And I just want to flash their pictures up front. In the audience is my trusty honorary C.L. Johnson postdoctoral fellow Niharika Shravan, part of the Boilermakers at Purdue University as part of my group. Just brilliant students and experts that I get to work with on a daily basis to tackle these pressing problems. All right, that's the introduction. The first thing I want to talk about is that we have watched stars explode. Okay. Up front is an image of a star, Sanduliac -69202. It's in the Large Magellanic Cloud. Now, has anybody been in the Southern Hemisphere before? Some people. Okay, for those who have, if you look up at the sky, first you see, oh my gosh, the constellations, they're upside down, right? And then if you look a little bit more closely, you may notice that there's these fuzzy patches. These two fuzzy patches are actually satellite galaxies, neighboring galaxies, the Large Magellanic Clouds. And in the Large Magellanic Cloud is this star. Now, if it weren't for the arrow, nothing would be really that different about this star from many others that we see in the field. Here we see something of comparable brightness. Up in the corner, something even bigger and brighter, right? But the arrow tells you something's going to happen, right? And indeed, on February 23rd, 1987, this is what was observed, okay? A supernova. The star had exploded. Well, actually, the star had exploded about 160,000 years ago, and it took that amount of time for the light to actually come to the Earth, which is something to think about. I mean, 160,000 years ago, modern man would have been evolved, probably not migrated out of Africa at that point. There's just a lot of history that has happened since then. But on February 23rd, 1987, it was sighted. Now, the naming convention, supernova, SN, 1987A. And then it goes sequentially, A, B, C, D, E, etc., right? So this was the first supernova of 1987. And appropriately, it was co-discovered by a Canadian. 1987, eh? I'm Canadian, so I can make that joke every time. By Ian Shelton. And one of the observing assistants, Oscar de Halde, at Las Campanas Observatory, have had the fortune of meeting and has told me the whole story of their exciting discovery. So that was the explosion. And then returning years later with the razor-sharp vision of the Hubble Space Telescope, there it is drifting in the center of the field. Let's do an enlargement here. Okay, the star has vanished. Now, for the untrained eye, there's a lot of structure going on. Don't be distracted by these rings. This was actually shed by the progenitor star system. What we think is not necessarily one star, but potentially two stars in orbit that flung off this material prior to the explosion. And this ring as well is also thought to be associated with the star prior to explosion. But in the middle, this debris, right, that's associated with the explosion itself. Truly, the star is gone. Sanduliac -69202 is no more. Okay? We're going to use this as a kind of a prototype to understand all the various supernova explosions that are happening in the universe in all their various forms. I like to put this up front. Why is this important? Why do I care? Right? And why should you care? So among other things, supernovae influence the energy balance, structure, and chemical makeup of galaxies. They can help trigger stars, new stars, so that one death can trigger new stars from forming. They're a major source of dust in the universe, and not the dust that you get on a table from not dusting for a while, but astrophysical dust. They produce a variety of exotic objects that maybe you've heard about before, things like neutron stars, which we'll talk about, black holes, and some gamma ray bursts. They produce copious neutrinos, this subatomic particle that we're going to come across later. They're progenitors of gravitational wave systems. So we've heard about maybe merging black holes. Those black holes came from supernova explosions. And as we'll learn, they produce gravitational waves themselves. And most important for us, they produce all the raw materials that make life possible. Right? So thus, as citizens of the universe, it's terribly important that we understand this fundamental process that goes on. Right? So to emphasize, I mean, the iron in our blood, the calcium in our bones, and the oxygen we breathe, love that oxygen, it's all thanks to supernova explosions. So have I gotten you some interest? Are you wanting to learn a little bit more? Okay, very good. I always find this helpful. So this is a little movie that's going to show a comparison of star sizes. And it starts off with things familiar like the moon. Okay? And it has some cool Harry Potter-like music associated with it. So there's the moon and Mercury. Mars, the red planet. Venus, hot. Don't want to live there. Want to live on Earth. Yes, we're there. Love Earth. Nice place to be. Step back and we see Neptune. Saturn without the rings, which is comparable in size to Jupiter. Okay, but now we're going to step back to some stars. The sun. And many people are surprised to learn that the sun is not a big star. It's not the biggest star. There are other stars like Sirius, the brightest star, is bigger. Right? Now Pollux. Now we're getting to an orange giant. And looking, we're getting bigger. There's the sun right here. Arcturus, a red giant. Aldebaran, another red giant. Now notice the color changes, right? Function of the temperature. Now Rigel, blue super. Whoa! Now we get back. The Pistol Star, we're going to get even larger. Antares A, we lost sight of the sun. It's long gone. U.S.A. And then
VY Canis Majoris, one of the largest stars in the universe.
Okay. And now we're going to zoom into along the horizon. And I think there's the size of Earth by comparison. And so just imagine this star exploding with us there, right? No, it's not going to happen. But that's the context, okay? The takeaway point is that the sun is actually a very modest-sized star, and there are a lot larger stars in the universe. Some other background material is understanding that the more massive a star is, the shorter its life. Okay? The benchmark is the sun. We take things in terms of the masses of the sun. So one solar mass is like the sun. And the lifespan of the sun is a healthy 10 billion years. But as we increase in mass, okay, you can see that the time frame gets shorter, such that around 10 million years, we're getting more towards, at 10 solar masses, we're getting towards about 30 million years. And then getting heavier towards 60, it's shorter. So in terms of stellar life, the more massive they are, the shorter, the more vigorous lifespan that they have. Also, the more massive it is, generally speaking, the different kind of remnant product that it may have. Okay? So I forgot to mention something, and this is very important. A lot of people get nervous that the sun will go this supernova explosion that I'm talking about, but that will not happen. There's a cutoff mass, somewhere in between here, maybe around 8 to 10 solar masses, and in fact, this is a discussion that we've had at this meeting, is determining what the critical mass is for core collapse. But it's certainly well above the sun's mass, so we will not have to worry about a fate of a supernova. The sun has other things in mind for us when it dies. Yeah, but once it reaches that supernova ability mass of about 8 to 10 solar masses, you can develop compact object like a neutron star, or if you're even much larger in mass, you may develop into a black hole. You have the gravitational potential needed to continue that collapse down into a singularity. Now, there isn't a one-to-one correspondence, and I'm going to put a caveat here. Another thing addressed in this meeting is that sometimes you can have more massive stars that have alternative pathways to becoming a neutron star. So it's fairly complex. But if you understand that there's a certain mass range for which you have compact objects of neutron stars and black holes, that's very good. Whereas more modest stars like the Sun will not develop these. They'll collapse into something like a white dwarf. Okay? And this can go on to a different supernova progenitor system, the type 1a supernovae that are associated with measurements in cosmology, which is not the focus of our talk. We'll be focusing on the more massive stars, about 10 solar masses and larger. Okay? Now, a lot of things can happen with these compact objects. They're highly compressed. Right? I mean, I could like sit on it and compress those neutrons to get as far as they could. And we have, because they're so far compressed, there are strong gravitational sources that can now be detected with gravitational wave facilities. The first hubbub was over the detection, thanks to advanced LIGO, of merging black holes. And maybe there is some discussion here at some point about that, right? And now more recently, they've been able to detect merging neutron stars. Okay, so these must have been two supernova explosions in close enough proximity that remnant neutron stars came into a final orbit. And what's exciting about these systems is that it's not just left to the gravitational wave facilities, but these emit in other messengers in the EM frequencies. So here we have gamma rays, and here we have an image with the Hubble Space Telescope. So this is a new era of multi-messenger astronomy. Perhaps you've heard of this. This is something that's gaining a lot of traction. Traction is very exciting, and something I'll come back to at the very end. Okay. What about my science, or what is it that I want to talk to you most particularly? One is, what are the types of stars that explode? In the supernova explosions we've come across, there's great diversity in their properties, in the chemical elements, in the amount of energy that they have. This can be traced to the type of star that gives way to the explosion. The other question is the physical one. How is it that stars explode? What is the mechanism that allows this process to take place? And we're going to get into the details about that a little bit. But these are the guiding questions that I'm going to provide context for. Okay? One is the single star scenario, right? And this has been one that has driven the community for a long time. But as we as we investigate the matter more in detail, we find that single stars are not the majority of the systems that we find. In fact, the more massive you get, the more often it is that a massive star has a binary companion. And this affects the evolution of the star. So this isn't getting into the question, what are the types of stars that explode? Now, I grew up in the age where this was the type of supernova progenitor system. But now we're getting in the age and trying to understand binary evolution. And this is why I've hired this brilliant Niharika Shravan to help me with this, because she understands this to much greater detail than I do. Okay? So it's a beautiful dance of the two stars as they go back and forth, and material can be drawn from one into another. And here's the statistic here. So more than 70% of massive stars will exchange mass with a companion at some point, leading to a binary merger in 1/3 of the classes. I've heard the analogy, actually, if you take two of these massive stars and you imagine them be about the size of a fist, and they start off at this distance apart. At some point in the evolution, the star will expand to such a size it will occupy almost this room in size. So certainly it'll consume the star next to it. Certainly that has effect on its evolution. The Hubble Space Telescope has played a critical role in identifying the types of stars that give way to the different types of supernova explosions. So here we have pre-explosion images and the actual supernova explosions on the right panel. So you can see that big blur. That's a bright source. That's a supernova. So what one does is, if a supernova is detected, can I go back to the scene of the crime before it happened, kind of rewind the tape, and look at the perpetrator? What star was there beforehand? So did Hubble happen to take an image of that field before the explosion took place? And indeed, Hubble has been able to. And it's been color-coded in a very clever way by Stephen Smart, such that red is indicative of a red supergiant, a red star. And you can see red sources here. So we can fit these with stellar tracks, which is to say, understanding the distribution of light across its wavelengths and how bright it is to constrain the properties of the star. Okay? These are the explosions where the ejecta contain a lot of hydrogen, hydrogen-rich supernova explosions. However, this process has been difficult for the stars where there is little hydrogen left behind, or perhaps none at all. Okay? That process that I showed of two stars dancing around, potentially one can give its hydrogen to another star, stripping it behind. And when we try to do the same game of finding the progenitor star in the locations of these stripped envelope supernovae, sometimes we come up empty. And it's happened a lot, so much that it kind of makes us nervous that we don't really understand what's going on. Now, patience has paid off, and we've been able to do this for a number of systems, but it's challenging. So here you can see a lot of pixels, but scientists can actually make use of that to try and make a little bit of a constraint about what kind of star was there beforehand. Here is a star that has been more stripped than these other systems, but you can see we're at the level, we're straining for information, but we can still extract it because Hubble has such great resolution at this level. You see those little darker areas compared to the surrounding? There's a star buried in there. We're able to understand its properties. And this is always amusing. Sometimes, this is the image, the field. Hubble has only a certain field of view, so you take an image. It's not necessarily the case that it'll cover the field of view. So in this case, we caught it just at the edge of the chip. And I can't tell you how many times I've gone through the archive to look at a supernova position and find it there instead. Not good, yeah. Okay, so that is the type of progenitor star. Let's think a little bit more about physics. Now, whenever I tell people I teach physics or physics and astronomy, sometimes they stand back and they say, I was never very good at physics, but I'm going to hold your hand and we're just going to go over the basic process here. A star starts off as a big ball of hydrogen. Okay? And at its center, all this gravity allows it to go through nuclear fusion, taking that hydrogen, producing helium. Okay? Now, when it runs out of hydrogen in the core, okay, then it has to start burning the helium that started depositing in its place because of this fusion. And then when that helium runs out, then it has to run to the next fuel. And so what it ends up doing through successive stages of nuclear fusion, you have this kind of onion skin interior. Now, this works until you get to iron. When you get to iron, this process of fusion is no longer exothermic. Do you know that name? So it no longer releases energy, it actually absorbs energy. So the core no longer has the radiative pressure it needs for gravity that wants to bring it together. That's the core collapse. Okay? Here there's a diagram showing, so we're near the core. There's originally a core collapse. Now, the core collapses, a lot of stuff happens. Okay? In essence, you have a lot of protons. So all these years of making heavier elements gets disrupted. You come down to protons, but they get squished down with electrons forming neutrons. Okay? This releases copious neutrinos, these subatomic particles that are released in the process. Okay? But it reaches to this point of neutrons, and the neutrons say, I'm not getting any closer together. Sorry, I'm making my space. So there's a bounce. So it reaches this neutron degeneracy pressure, and then it tries to, it bounces off that. It's a hard core. Now, it was thought that that would be what would drive the supernova explosion. But decades of simulations have shown it just doesn't work. So it comes down to this neutron core, neutron-rich core, bounces, but then all the material of the star still continues to push onward on it. It needs an additional heating source to reinvigorate the shock, to push it out and disrupt the star. Okay? We think that heating source is largely associated with the neutrinos that I mentioned. So these are these subatomic particles produced when these protons accept electrons and through the process of photodisintegration. Okay? That's one idea. And so there has been a series of simulations to try and harness that idea. Okay? That there's either copious neutrino production that aid in revival of the shock, or if there was enough rotation to begin with in that neutron, that proto-neutron star in the beginning, that rotation can be associated with strong magnetic fields that set up a symmetry axis that can drive a jet, okay, and totally disrupt the star in another extreme scenario. Okay? So that's the jet scenario. Here we see this is the core of the explosion. This is in terms of, think of this in terms of, here's the boundary of the shock. Material is coming in. We see the sloshing back and forth. There's heating by these neutrinos, okay? And it goes back and forth, the sloshing, and something that they call the standing accretion shock instability, SASI, it's a great name, back and forth until finally it can disrupt the star. Case in point, though, can you see that there's a difference in the morphology between this and this? Okay? Keep that in mind as we move forward. Okay? In order to be able to explore that mechanism of the supernova, we need a lot of examples, and we need to get good at finding supernovae. Supernovae, thankfully, happen pretty often. They happen at a rate of approximately 1 per galaxy per century, maybe 2 per century. And if you listen, you can hear one going off every second in the universe. No, you can't, but it is actually happening. Approximately once every second, there's a supernova that's going off in the universe. Okay? Now, clearly, we don't have access to a lot of them, but a lot of them we do. Right? And here is actually postage stamps of the many supernovae discovered in a particular survey. And you can see them all as point sources in their host galaxies. Okay? Here are some of the efforts that are trying to find supernovae. This Pan-STAR survey that I was associated with, the Assassin survey, Palomar Transient Factory, now known as the Zwicky Transient Factory, run largely by Caltech, and an army of amateur astronomers that I work with. By day, Stu Parker in New Zealand is a dairy farmer, and he's a great guy. He knows all 700 cows by name. But by night, instead of buying fancy cars, he's bought some really nice telescopes, and he helps in the discovery of supernova explosions. I don't know if we can get the lights down, but people here, do you think you can spot the supernova? Can you see where it's developing? Somebody sees it? Right there, that's right. You're right, that's right. There it is there. Okay, so clearly this is an inefficient process by just looking at it visually. And these days, what one does is look at and by the way, what was happening here, we take an image of the sky at some point and then return sometime later, months later, weeks, days. Currently, we're at the point where we're monitoring hourly, almost, in some fields, to look for changes. Instead of doing it by eye, you use computers to take a subtraction of one image from another, and you look for a difference. Right? But still, there's a rich history of people finding supernovae by eye. And I just wanted to give you a flavor of that. Here's another scenario. So this was images donated by Stu Parker. And here you can see this tiny, adorable spiral galaxy and then sometime later, boom. All right? Now, to some, it may not look like much, but recognize that this is a galaxy, let's say something like the Milky Way, with 100 billion stars or so, and this fuzz is actually just, the nature of many stars that are spaced out, and then all of a sudden, one of those stars explodes and becomes as luminous, with a luminosity that rivals the entire host galaxy. Right? A supernova can be brighter than billions of stars put together. It's quite remarkable. What's also remarkable is when this happens in our own neighborhood. Okay? We live in a galaxy with stars, with lots of massive stars. So obviously, every so often, something has to happen in our own backyard. Right? And here I'm showing a well-known engraving of Tycho Brahe, or Tycho Brahe, who spotted the supernova of 1527. When galactic supernovae occur, they can be visible for many months, maybe even over a year, and they can even be visible during the day. Right? There are stories about people reading at night to the light of a supernova, and all the confusion and people being afraid of this source that came out of seemingly nowhere. But Tycho Brahe was prepared because he had the right instruments to be able to make measurements of the system. So we're going to do that. Okay? And we can now go there today, again, with razor-sharp vision of Hubble, but in this case, it's actually Chandra X-ray Observatory, and look at what it looks like today. Okay? And here we see the Tycho's supernova remnant, or the supernova of 1572. Okay? And I wasn't able, he wrote down in his log, and then which turned into a book, this entry, and I wasn't able to skim it down, so it's quite amazing. Here, let's emphasize here, a miracle indeed, either the greatest of all that have occurred in the whole range of nature since the beginning of the world, or one certainly that is to be classed with those attested by the holy oracles, the staying of the sun in its course in answer to the prayers of Joshua, and the darkening of the sun's face at the time of crucifixion. Thought that appropriate close to Easter. I mean, it was either the most important thing that ever happened, or like the second most important thing that ever happened, right? Now, interestingly enough, not that many years later, there was another sighting by Tycho's assistant, Johannes Kepler. And by the way, there's a whole personality of Tycho Brahe I would encourage you to investigate. I mean, the one that comes to mind right now is that he lost a portion of his nose in a duel with somebody at a wedding over a mathematical formula. Okay? Now, Kepler was hired by Tycho Brahe to help him with all the measurements of the planets that he had done. And the relationship was fraught with tension because Tycho had decades of observations, but he only gave them in little pieces to Kepler. And Kepler pleaded, please give me the data, but he wouldn't. He would give it. Now, Tycho died less than a year after they started working together. So there's a little bit of gossip about how did that happen? How did Tycho Brahe come to such an accelerated death? They actually exhumed the body of Tycho Brahe to see if he'd been poisoned, to see if they could find evidence of poison in him, and they didn't. So Kepler was cleared on that account. Anyhow, I'm distracted. I'm sorry. There's a lot of historical anecdotes here. Kepler, in 1604, spotted another galactic supernova. His take was a little bit different. The star's significance is a difficult matter to establish, and we can be sure of only one thing, that either the star signifies nothing at all for mankind, or it signifies something of such exalted importance that is beyond the grasp and understanding of any man or woman, let's say. So either it's most important, or let's move on. Nothing here, right? Okay. And where's Frank? We're timed for about 8 o'clock-ish, or... Okay, all right. I will try not to try your patience. I've gotten distracted, but I'm having a lot of fun.
The only rule is we include the questions, we got it off, we cut off at 9
Oh my goodness. Okay, I will definitely not keep you here that long, but thank you. Thank you for the info. All right, we saw this earlier. Okay, Crab Nebula is shown a lot. This is the remnant of a supernova explosion that happened in 1054, and we have that date chronicled by the Chinese, so we know that it happened on that time. It's quite beautiful. This is a Hubble Space Telescope image, largely sensitive, so this is optical emission, but cherry picking, like the demonstration that you showed, at certain wavelengths, and then you combine them in the right way to make a pretty picture. This diffuse emission is associated a lot with the neutron star that is rapidly rotating. We call it a pulsar, because in this case, every 30 seconds, there's a strong wave of energy that comes in our direction. It's illuminating this pulsar wind in the middle. And around it, okay, is other ejecta. I want to highlight this. It's an energetic phenomenon. So here we're looking multiple years. Beautiful work by, again, another quote-unquote amateur astronomer. I mean, this would put professional astronomers to shame. To get this stable image over these multiple years, and you can see the swirling, right? Remember, this is a rotating effect. You can see it pushing out the wind around it. It's almost looking like a living thing. Right? All right, one thing I want to capture for you is that when we look at objects like supernovae and supernova remnants at different wavelengths, that often means different space telescopes or ground-based observatories, we capture different physics, and that usually is reflective of different temperatures and densities. So we have the Crab Nebula there. You can see a different take, but when we look at radio or Spitzer in the infrared or Hubble in the optical or Chandra at X-ray wavelengths, okay, they're all privy to another piece of the remnant. So in order to do a comprehensive investigation, we want to try to utilize the full span of the electromagnetic spectrum. And to give you a little bit more, I mean, each of these supernova remnants needs its own origin stories. This is a remnant in the Small Magellanic Cloud. We have no confirmed sighting, so we can't pinpoint the date. So we have to use other means to estimate the date, and we think it'd be larger than 1,000 years ago. Here's something different. Again, we don't have a certain date of explosion, but we know it to be over 1,000 years old, and it's a combination of wavelengths. This one now primarily a Chandra X-ray observatory. We don't know the date. It's fairly old. And then this. Okay? I showed the multi-wavelength image. We'll come back to that in a moment. But this is the Hubble Space Telescope image. And a shout out to Arfizan, who I think is watching right now, who is responsible in arranging these observations to make this beautiful mosaic. So what are we looking at? The debris of a star that exploded about 340 years ago. The red is sensitive to sulfur-rich material. The green is oxygen-rich. The purpley blue stuff, that's actually associated with the star before it exploded and the material it released to the surrounding environment. We're going to go back to the multi-wavelengths. So now we're not just looking at HST, but we're looking at Spitzer. We're also, and that's infrared wavelengths, and we're also looking at Chandra at various wavelengths, sensitive to different parts, different elements. Okay? The X-ray here is sensitive to iron-rich material of the supernova. There's different kind of things that we can point out in the anatomy of the supernova remnant. At the periphery here, do you see this thin band? Okay? This is actually associated with the original shock wave of the supernova, right? You can imagine explosion has a shock wave, and that's the forefront of it, and we've been able to watch it with time expand. Okay? Also, in the center is that neutron star. Right? The core collapse, the material being compressed down to such densities that would have neutron-rich material. If we could get the lights down on this, here is time lapse of about 50 years of images of Cassiopeia. And you mentioned Joe. Joe helped create this. We scanned in plates dating back decades, and we smoothly transitioned into a Hubble Space Telescope image at the end. And you can see the remnant expanding. And so my PhD thesis was largely done on Cassiopeia. I'm grateful for doing it now-ish, because if I had done it 50 years ago, it just wasn't nearly as bright as it is today. And the origin of this heating has, let's just say, as the shock wave moves out, there is another shock wave that propagates in the opposite direction with respect to that forward shock wave that heats and excites the optical emission that we see today. So what can we do? I want to understand how this thing exploded, and I tried to point out those simulations and the extremes in the morphology, right? So being clever with our spectra and measuring velocities, we can do a three-dimensional reconstruction of the remnant. And this is kind of my niche. This is something that I'm trying to get at. I'm looking at the large-scale structure of the remnant and try to piece together how the bomb exploded. Okay? It's like a bomb scene investigation. I go into the room and I look around. Did it explode equally in all directions, or is there a preferential access? And then I can go and scrape off bits and pieces of the bomb and do a chemical analysis to understand what it was made of. This is kind of what I'm doing now. This is thanks to my contributors. I honestly got this about an hour ago. None of my grad students, and not even Niharika, want to travel to a supernova in space to study it. So we're making a virtual reality environment for which to study it safely, I guess. So as you can see, they have the goggles on. So we have this collaborative environment, right? So we can see that's Jordan who's helping out right now. I wish I was there with them. But with virtual reality, at some point, I will be able to do it remotely. So here we can see we have all these people together. We're making a collaborative virtual reality environment. It's both a teaching tool and an area of investigation. There's the avatars, so you can see their faces. So that's what they're seeing right now. And he's sketching out in real time the large-scale structures that were being shown in that animation. Okay? I mean, as an investigation, I can look at pictures of a crime scene, but unless I go there, right? That's the only way to really understand what's going on. And I can't go to see Cas-A, so I'm going to bring it into my laboratory. Oops. Great. So one thing is visual. The other thing is to be able to compare it with simulations. And that's something that we're doing also. So this is a simulation. That, you know, that sloshing you saw back and forth. Okay? They've advanced those and taking snapshots. This is seconds after explosion and hours after explosion. And the blue is representative of nickel-rich material, very heavy material, that roughly translate into the iron-rich material that we see in Cassiopeia. And the large structures that we see in Cas-A, and I didn't get a chance to talk about it, but you see a large ring in the back there? That's where a large deposit of iron-rich material is. This is giving us insight into the explosion, which is to say that it's not homogeneous, it's not this sphere that is exploding, but it's messy. And it's dominated by a few instabilities where you have this nickel-rich material stream out ahead of the lighter elements. Okay. Coming on to the good stuff now. Remember I said to be able to do our investigations, we have to look with the right wavelengths. Right? So now this is X-ray, but now enhanced around the silicon lines. And now, hold on, I told you that this was a morphology that's consistent with this neutrino kind of instabilities. But now we see something like the other model. Do you remember that? Kind of like the jet model here. Okay? And again, help with the Hubble Space Telescope. We took images purposely along that direction and tried to follow material out as far as it could go. And now I'm going to zoom in here. So images separated only a year apart. And you can see this is stellar debris being flung out over 15,000 kilometers per second. Right? Those with sharp eyes may notice funny things like this. Do you see how that pops in and out? Okay. All that means is that it's running into some kind of overdensity in the surrounding environment and lights it up. Is that saying time out? Oh, somebody's making their way. Okay. as that passes on. It's actually a good soundtrack for this, right? Okay. But ladies and gentlemen, this truly is, okay, this is raw material for future stars, future planets, maybe life, okay, being seeded in surrounding interstellar space. We're watching it happen here. Okay. Debris. This is actually sulfur-enriched debris, but it has other chemical elements. There may be, heavy elements in there, yes. Star stuff, that's right. That's going to go support the manufacture of new systems. Okay, so now we're going to go into what we're looking to into the future, what we anticipate to be investigating in the future. I show this plot up, and let me take a second to explain it. This is time, okay? And this is how bright the system is. And remember I said how supernovae are designated by the year that they're discovered. And this is a system called Supernova 2009 IP. Now, it's a dumb name because the supernova actually took place in 2012. Okay? Now, why did it get 2009? Well, in 2009, people jumped the gun. They saw that it got brighter, but it didn't quite get the brightness, the luminosity needed for a terminal explosion. Okay? Actually associated with the system, maybe you've heard of Eta, a star that ejected a lot of material all at once. And then it went down, but people were clever to monitor it with time. And then, monitoring the light curve, we saw a lot of fluctuations leading up to the final core collapse explosion, potentially. The thought is that the star, as I said, had some kind of major eruption like Eta. Now, this is a dramatic, mega example, but maybe something like this has happened in that other thing, where the star's death was preluded with a giant eruption. Okay? That becomes very exciting, because now we're at the point where we may be able to predict supernova explosions. Okay? Now, when I sat in public lectures like that, and I still do, but okay, when let's say about 20 years ago, I remember looking at a star, you'd never be able to know when it's going to explode because all that activity is happening at the core, right? And it takes tens of thousands or hundreds of thousands of years to evolve. And yet, in this case, we see things happening, right? The star is signaling its demise with this pre-stellar activity before the actual explosions. So what we're in the position of doing, and what we have done, is when one of these supernova imposters happen, we can continue to monitor the system and wait for the supernova to happen. We can predict stellar explosions. We will someday. Okay. Important caveat to that. If you believe the story that precursor activity is associated with the launching of a stellar envelope, the transmission of information from the core region, core collapse, to the envelope means that stellar interior must be perturbed. So this onion skin interior that I showed you was fine enough for main sequence, but towards the end of the star's life, that is not what it looks like. It must be much more turbulent and dynamic. Okay? And the explosion is taking place here into this turbulent progenitor star structure. Okay, now the last couple slides, and then we'll end it off. I've set up for you the motivation for understanding core collapse supernovae. I've talked about the types of stars that explode and trying to understand the explosion mechanism. Okay. I've actually made life a lot more difficult for myself because not only do I need to understand the origins of that core collapse, whether it's purely driven by that neutrino instability or the jet-driven, but now there's added mess by the progenitor star structure. How am I going to be able to tell which specific processes lead to the explosion and the remnant structure that I see? Okay. There's a couple of facilities that are coming online or that are online already that you, the taxpayer, are helping to support, so you should be aware of it. Okay? One is a Large Synoptic Survey Telescope, LSST, which is being developed in Chile. This is going to come in online around 2021, 2022, depending on how things go. Okay. Now, we already have surveys, sky surveys, which I mentioned. This one will have a unique depth, so how faint it can see objects, and how routinely it will be mapping the regular sky. The cadence has yet to be finalized, but let's just say every 3 to 4 nights it will return to the same piece of sky, different filter, but it'll return and then image again, image again, image again. And it'll do this for approximately 10, maybe longer years. So it'll be sampling with such regularity that we'll be able to potentially trace this kind of precursor activity. I failed to mention before that this is kind of the only light curve that we have that is able to sample such back, because there's a large divide between the supernova luminosity and the level of this precursor activity. And actually, we saw a talk today by a very bright grad student at Caltech, Anna Ho, who showed, hey, I got something like this because of the Zwicky transient factory. So we're inching towards this notion of if a supernova goes off, let's look at what's happening beforehand to get a sense of what the star is doing. And can we connect that to the explosion? The other way that we're going to be able to do it is, as I said, multi-messenger astronomy. So not just looking at the electromagnetic spectrum, which has been the focus of the talk here, but now we have facilities sensitive to gravitational waves and neutrinos. Okay? Gravitational waves, there's a lot of jargon in here, but let me just say this. Instead of trying to ascertain what's happening at the core of the star by way of everything that's happening around it, gravitational waves and neutrinos are coming from the heart, and they're unimpeded by the stellar ejector around it. So we're getting direct live information about the core collapse as it's happening. Okay? This is going to revolutionize our understanding of supernova explosion. I cannot underestimate the amount of excitement that the people have, and all my students use animated GIFs for expressing excitement, so this is what I chose here. Okay. Going back, remember that first supernova, 1987A, right? There were neutrino facilities operating at that time, and they detected approximately 20 neutrinos. These are very difficult. There are neutrinos passing through us right at this moment. They normally don't interact. You need to have a lot of stuff, a lot of tanks of water. They're often underground to be able to make these detections. Here is, and to give you a sense of the difficulty, so this is in minutes, okay? And just can you imagine the flat line for years beforehand, waiting for the 10 seconds for which the 20 or so neutrinos came through. But from those 10 seconds, okay, and those 20 neutrinos came, I've heard, anywhere from 500, 600, 700 scientific papers that were published on it, because each one were so valuable in understanding what was happening at the core process. I mean, that truly was verification of our model of a core collapse forming the neutron star, because the neutrinos were produced in that process. Okay? So we've come some time. We've developed quite far from the original facilities. With present facilities, we will detect thousands of neutrinos from the next galactic supernova, okay? And there's much more rich science to be able to be done. I'm affiliated now with something called the Supernova Early Warning System, SNOOS. So the idea is, if this is our galaxy and there's a supernova that happens on the other side, the first messenger to arrive on the scene will be the neutrinos. And there they'll be streaming. Everything else will come afterwards. The gravitational waves will be around there, but it's likely that the gravitational waves will not be as strongly detected as the neutrinos, because just the way it all works. And there we are detecting it, right? The neutrino community will give the rest of the world, depending on the type of star, it could be as small as minutes, tens of minutes to hours on, hey, something big's really happening, right? And they're going to be sending alerts. We're working it all out to find what is the proper communication channels, etc., to alert the world about the next galactic supernova. Now, we could be waiting a while. I'll admit that, right? It could happen tonight, or it could happen when I'm not around anymore, right? We've been waiting some time. And with statistics, unfortunately, there were two of these type 1a supernova explosions, the Tycho's remnant and Kepler's remnant, that happened fairly closely within one another, but we've been waiting a couple hundred years for another one to take place in our own galaxy. 1987A kind of counts, but it was in a satellite galaxy. We'd like something to happen now. But thankfully, with the neutrino and maybe even the gravitational wave facilities, even if a supernova galactic one happens on the other side of the galaxy, it has to go through this messy swamp forest of dust that could minimize the light that we see in the optical, the one that we're familiar with. So it may not be visible necessarily to the naked eye, but the neutrinos and the gravitational waves will certainly catch it. Okay, well, with that, ladies and gentlemen, I think if you looked in the far west at twilight, you may have been able to see Orion, but you might have to wait until the winter to be able to see it again. But in the armpit of Orion, we have Betelgeuse, and that's kind of one of our favorite stars that we like to think about as the next supernova candidate. So when that happens, next time it's visible to you and you notice it, have a look and think about all the things that I've discussed. I mean, the fact that it's one of these fundamental processes in the universe that makes life possible, and all the exciting science that we're doing behind to understand it in all its full glory. Thank you very much.
We need to make sure that we ask the questions for the online audience, so I'll repeat it into the microphone.
Okay.
All right, questions? Yeah.
Hold up, online
Oh,
audience.
you've got the microphone. Oh, good.
Ready?
Okay, good.
Okay, in the graph of 2009 IP,
Yes.
when it gets to that far right peak, is that by definition a supernova, and is it just the luminosity that defines it there, or are there other things? So what I'm guessing at is that will sometime in 10 years, it'll go up another 50% above that point. Is that possible?
I was hoping somebody wouldn't ask a question like that. For a public talk, I like to give clear explanations, but you're actually hitting on a very important point. Okay? It's not 100% clear of whether or not this was the terminal explosion of the supernova. You're absolutely right. Okay? There's a lot of circumstantial evidence that suggests that the supernova is actually this small peak, and then this is when it ran into, this is luminosity generated as it ran into this precursor activity. Okay? That's one of the understand. But depending if there are other experts in the room here, they would potentially argue that this was actually the supernova, and this was just a minor eruption before the actual supernova explosion. But you make the point. But you make the point that this may not necessarily be the terminal explosion. It's possible that sometime later it may do something else. But to be fair, it's considered to be the more unlikely scenario.
But it's only 3.5 magnitudes difference between your peak and the 2009 peak as well.
Supernova. So this was just above.
It's almost 15.
14, and that's 3. Yeah. So this was exciting because it became the anticipation was that it would continue to get higher, and then this low-level activity. I mean, this is where the large difference is.
Okay.
Okay, the reason that came to me was that this graph has a striking resemblance to the net worth of Tesla's stock. I have one more question. With the neutrinos and the gravitational waves, what is the speed of propagation through space for those two? Are they identical?
Speed of light. They should be propagating through.
Both are at the speed of light.
Yeah. Near speed of light, I would say. Yeah.
Okay, so you got one way back there and one over there. You choose. Okay. Grant, you got the mic. You're in charge.
I'm the grand poobah of the mic.
So neutrinos, I don't remember the mass that we've given the neutrinos, but it's an extremely small mass, so it's just slightly slower than the speed of light, right?
That's right. Thank you for.
Just wanted to fill in while
Gravitational wave, that's radiation, that's, speed of light. But then the neutrinos, believed, has a bit of a mass, so
Tiny
that kind of
mass.
slows it, yes.
So, just an amateur science fan here, but we have all these constant supernovas going off all over the universe. Why isn't the sky just filled with clouds of nebula everywhere? Like, what causes them to fade away, or, it would seem like they'd be all over the place.
Well, I'll tell you, if you had eyes with the right resolution and wavelengths, you would see remnants of supernova explosions across. If you look at, there's different surveys depending on what you do, but I'm very familiar with survey that's sensitive to light of hydrogen alpha transition, okay, hydrogen gas. You see these very large round blobs of sorts across the galactic plane, okay, and this has all been carved out by supernova explosions. Yeah, so they are there, absolutely. You just need to have the right resolving power and wavelength to see them.
Okay, so we have a question from online. It says, what was the toughest part of getting the debris field into your virtual reality?
Oh, okay. Well, let's see here. So I think the most difficult part of creating that data set was just the man hours. Dan hours, I should say, yes. So I think that I went on observing trips over several years. I think I must have banked at least 4 weeks of my life at a telescope to make those measurements. And then, 5 years of my life in front of a computer to reduce them to make them the construction that you see. And actually, the measurements were simple enough. This is just an aside. But the visualization, finding the right way to do the shadings and to make that skin representation, that took a lot of time.
Okay, we've got it next.
When a supernova explodes, almost all the matter is ejected, and the neutron stars are collapse of matter. What is the radiation source that generates the light from the neutron star?
The light of the neutron star. Okay.
Yeah, where is that coming from? If all the elements down through iron are
Okay.
blown away.
So let me try and make sure. So the neutron star itself is something separate from the ejecta, and the ejecta, depending on the type of remnant. So in the case of the crab, the ejecta may be illuminated by that neutron star, which has a rapidly which the neutron star itself is rapidly rotating and has a strong magnetic field, and it can accelerate particles nearby that can excite the surrounding ejecta. The neutron star itself may have a temperature associated with it, right, and emit like a black body, so that would be its energy source.
They're making you work, Grant. Next questions are in the exact opposite corner of the room. And then, of course, you've got pulsar emissions from a neutron star. You want to fill those while we wait for the microphone?
That's associated with the rapid rotation, the development of an axis, and you may have beaming of these highly accelerated energy towards us, depending on the orientation.
Earlier, you mentioned that you gave an example of using your two fists to think about two stars that are a similar size, and then one consumes the other. And I'm wondering how, if both stars start off roughly at the same size, what determines which star consumes the other?
Oh, well, may I defer to Niharika, who's the stellar evolution expert?
Hold on.
Hold on.
Hold on, wait for the
Yeah,
wait for the
please,
microphone.
please do.
Online audience.
All right, that's an excellent question.
Yes.
And as such, we only begin to start to understand what happens when two stars interact. It's very complicated. So usually you would not expect both stars to be of the same mass. There would be marginal differences, in which case, if you remember Dan's, one of the slides in which he had said that there is a mass, when you were going down in mass, that's the longer you live, right? So the lower mass stars live longer, and the higher mass stars evolves faster, and it becomes big. So because it becomes big, it has a tendency to transfer mass in one direction preferentially. So in a world where both stars were of the same, they would sort of engulf each other, and that can also happen in complicated physics. But usually the more massive star, because it's faster to evolve, it'll be the one that'll transfer mass. But if you want to know more, find me after the talk and I'll tell you everything.
Okay, one more question from online. It says, how close to Earth does a supernova have to be before we have to worry about the dangerous cosmic rays and other things? In other words, if there were a supernova a certain distance away, it could cause some problems here.
Yeah, and
what's that distance?
And certainly it has. It has affected Earth's evolutionary status at some point. There's a lot of caveats to that, which is to say, depending on the type of supernova explosion, and whether or not a jet is beamed towards us. But I can say I use the example of Betelgeuse. If Betelgeuse were to explode, it would cause non-negligible influence on us. And I worked out this number sometime because somebody asked me this before, and I don't have it prepared. But there's a great book by Craig Wheeler, who was at the meeting today, Cosmic Explosions, that goes into detail about what happens here on Earth if Betelgeuse explodes. But I know that's a good example. So we can watch basically safely from Earth's vantage point about Betelgeuse, but it would cause some kind of noticeable changes here.
All right, so the internet says Betelgeuse is 642 light years away.
Yes.
Okay,
Yes.
so
So it's
somewhere 600 or so light
if
years away.
if you hear that it's 10 parsecs away, you better crawl under any hole or anything.
But they won't understand parsecs, right?
That's right. 30 light years, sure.
We have a question way back there.
So if the neutron star is a possible result of the core collapse, I don't even know if quark stars are a real thing or science fiction, but I've heard of them. So would that result from the same kind of process, just a slightly larger precursor star?
Yeah, we had a couple of questions online as well. Could quark stars result from this?
Right. I didn't know, but I should have known, right? I'm unfamiliar with that literature, but I do know that has been posited. I mean, if you have neutron-rich matter, why couldn't you have some strange quark matter as well? And I know some scientists have tried to explain some of the interesting phenomena we observe in supernovae by these transitions into quark matter. Yeah.
Okay, I've heard other people say that they felt that the quark matter would be unstable, would go straight down to a black hole.
Well, I don't want
to get a stable form of matter in there, but I'm not.
I didn't want to make a judgment call. I was being neutral, but yeah, it's not a predominant.
I'm okay with speculating, okay, because it's not my field. All right, you're going to get the last question because we're almost at 9:30. So, go ahead, Cal.
You got a chart up for supernova 2009 IP. Have we found similar patterns that are enabling us to say, we got to watch these guys real soon?
Right. Excellent question. And I tried to make that point in that we have such scant details at the moment. This is kind of pointing us that direction. I was associated with another object where it had this luminous outburst. Okay? We continued to monitor it, and 9 months later, there was a supernova explosion. So it is happening. But I mean, I could count all these events on my hand, the fingers on my hands, as far as how many that's happened. Even just one hand, I think, yes. Right. But the point that I was trying to make is with these new facilities, the hope is that we'll have not just this hand, but all the hands in the audience as far as examples of this to be able to make real anticipations. Maybe there's certain patterns related to the explosion that we can exploit.
Yeah, and this is just and this is just one example of how time domain astronomy is taking off with things like LSST. It's going to change a lot in the next decade. All right, you can get that one follow-up question in real quick.
Now, they're collecting neutrinos to try to predict when, or maybe find out when this next thing is going to happen, right?
That's the hope, yes.
But
we have a short turnaround.
Any direction.
We're working on that as well. Triangulation amongst the various facilities. We put in a proposal for the National Science Foundation. Maybe they'll give us some funding to do that, but that's the idea.
I just have to comment that for the online audience, that the question inside was about neutrinos and that not getting a directionality, but yes, triangulation can do it. Okay, we've got to stop, folks. I know this was a fascinating talk. Give them another big hand.
Again.
All right, we'll see you here in 2 weeks, the fiery fate of exoplanets. Good night.
Thank you. Hey, thank you. It's great.